Hi everybody, thanks for watching. In this video, we're going to tell you about a really important word in the world of thermochemistry called enthalpy. So let's begin just by giving a really simple definition of what enthalpy is. Actually, everybody kind of already knows what this is. You just don't know that we called it enthalpy, because enthalpy is really just energy released or absorbed as heat when physical or chemical reactions happen. So any reaction you can think of, such as lighting a match, where energy or heat is given off, we call that heat the enthalpy. So the next thing you need to know are some of the symbols and units that you'll see when working with enthalpy values. The first one is the symbol we use to represent enthalpy is delta H, or change in enthalpy. The capital H is what means enthalpy. The typical units for enthalpy are kilojoules per mole. Remember, if enthalpy is supposed to be heat energy, then kilojoules makes sense because those are one of the units that we use for energy values. When you see an enthalpy value for a reaction, you'll see the equation written out first. Following that will be delta H, or change in enthalpy, equals, then here's the number, so that's the quantity of energy released or absorbed in kilojoules as this reaction happens. Now you may have noticed with the delta H value given with 286 a negative sign. There are some sign conventions you have to get used to when you see enthalpy values. If your delta H is listed as negative, all that's telling you is that the energy is being released. You might remember this when you were writing your Q equals Q expressions, where one of the Q values was negative when it was releasing heat. It's the exact same thing here. The name given to reactions that release heat with negative delta H's is exothermic. There's also some reactions that absorb energy. This means that they're going to feel cold when you touch them, like instant cold packs. Those will have positive delta H values and are called endothermic.
So where do we get this negative 286 kilojoules from? During a chemical reaction, bonds in a reactant need to be broken. So in this example, we have hydrogen and oxygen joining together to make water. In order for this reaction to take place, the bonds between the two hydrogens and our oxygens need to be broken. When that happens, the reaction requires energy. So energy is absorbed from its surrounding. How much energy does it take? In order to break these bonds, we need positive 300 kilojoules of energy. Then, as the atoms rearrange into products, new bonds are formed in order to form these water molecules. So when this happens, this gives off energy. So energy is going to be released into the surroundings. In order to form these new bonds, it's going to take negative 586 kilojoules of energy. So where does this negative 286 kilojoules come from? If you take the amount of energy it takes in order to break the bonds and add that to the amount of energy it takes to form the bonds, you're going to get your change in enthalpy, which is negative 286 kilojoules.
So let's take a look at another example where you can calculate the enthalpy change by looking at the bond energies like we did here, the amount of energy to break the bonds versus the amount of energy released when you form the bonds. In this example, we've got H2 reacting with Cl2 to form two HCl molecules. If you're going to use bond energies, the first thing you need to see are the bonds themselves. And the best way to do that is to draw out the Lewis structures for each molecule. So here we have H2, Cl2, and both HCl's. And once you've got your Lewis structures drawn so you can actually see the bonds, all you need to do now is look up the energy values for each. If you start with the hydrogen to hydrogen bond, you can go to one of these tables that gives you a whole bunch of bonds listed out and the energy values they have. So for a hydrogen-hydrogen single bond, you can see the energy is 432 kilojoules per mole. If you do the same for a chlorine to chlorine single bond, it's 243, and all you have to do is add those two numbers together to get the total amount of energy required to break both of those bonds. And in this case, that is 675 kilojoules total to break the bonds. And then you do the same thing for the bonds and the products that are being formed. This time we have two separate hydrogen to chlorine bonds. If you find that on the list, it looks like we're right here. That bond energy is 431. Just notice I'm going to add that 431 in twice because both bonds have to be formed. The other thing we have to remember to do is make those values negative because when you form bonds, energy is released, not absorbed, and we have to show the release with a negative sign. The same steps follow. Add up your two negative values to see the total amount of energy released. That total being 862 kilojoules. Notice the negative sign again to show that it's being released. And the final step is to take your two energy totals and simply combine them. 675 plus the negative 862 gives us our final enthalpy value that could be plugged in right here of negative 187. We also now know that this reaction is exothermic, releasing 187 kilojoules per mole of heat energy.
There are many types of enthalpy that involve breaking and forming bonds, so this would either result in releasing or absorbing heat. The first type is enthalpy of combustion, and that just happens when substances start to combust, and usually resulting in an exothermic reaction. The second type is enthalpy of a solution, and this is when heat is either released or absorbed when substances tend to dissolve. Usually this happens in an endothermic reaction.
Another type of enthalpy is called enthalpy of fusion. This is what we call the heat absorbed when a substance is melting, such as a solid turning into a liquid. These have typically positive enthalpy values because to melt things, energy has to be absorbed. There's also enthalpy of vaporization, which is the heat absorbed when a substance vaporizes, such as water liquid changing into water vapor. These are also going to have positive enthalpy values because when you vaporize a liquid, it requires energy also.
It really doesn't matter what you call it because all enthalpy values mean the same thing. It means whether heat is being released or if heat is being absorbed.